Whenever there's a lottery, the odds of winning are given. If you go to a pizzeria, they may tell you the number of possible pizzas that can be made given their toppings. If you have a combination lock, it's secured because of the number of different solutions that are possible. All of these things might seem different, but they're all part of the same branch of mathematics. Learn more about permutations and combinations and how they work on this episode of Everything Everywhere Daily. In a world filled with endless information, there remain some things that just can't be explained. If you're intrigued by the mysterious, you'll love this podcast, One Strange Thing. One Strange Thing searches the nation's news archives for stories that can't be entirely explained. The podcast unfolds regional tales of the mysterious, the paranormal, the unexplainable, and the delightfully weird. Was the mysterious blob that appeared in Texas a virulent fungi or an extraterrestrial? What happens when a police chief answers a mysterious call about a ghostly sighting of a metal man running down a rural road outside of town? One listener described the show as like Ripley's Believe It or Not in podcast form. The humor is wry, gentle, and delightful. I recommend you check out a recently fascinating episode of theirs on the Midwest's most famous version of Bigfoot, the Grassman. Come explore these delightfully weird stories on this spooky yet funny podcast. Find One Strange Thing on Apple Podcasts, Spotify, or wherever you listen to this show. This episode is sponsored by Noom. You've probably seen any number of weight loss fads over the years. They come and they go. But when it comes to weight management plans, you don't want a flash-in-the-pan fad, you want a long-term solution. And that's Noom. You're probably aware that a lot of weight programs out there focus on what you eat. Well, Noom is using science to help you understand why you eat. And that makes a huge difference. Noom takes a psychology-based approach that helps you build better habits and behaviors that are easier to maintain. Noom helps you understand the science behind your eating choices and why you have those cravings. And the best part is that you decide how Noom fits into your life, not the other way around. Noom's personalized courses are easy to follow and will help you grow your confidence with tools you can put into practice on day one. They'll give you the knowledge and wisdom you need to make informed choices about what you eat. Based on a sample of over 4,000 Noom users, 98% say Noom helps change their habits and behaviors for good. Sign up for your trial today at Noom.com. That's Noom.com to start your trial today. If you're not familiar with permutations and combinations, do not fear. It's a subject that often isn't covered in basic mathematics courses, but it also isn't that complicated. It involves nothing more than basic multiplication and division. It doesn't necessarily even involve fractions or decimals, just whole numbers, and they can usually be explained using everyday things that you're familiar with. So to start this discussion, let's take a very simple case. How many ways can you arrange the numbers 1, 2, and 3? This is a pretty small number of things, so we could just brute force this and write them all out. There are 1, 2, 3, 1, 3, 2. 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So there are 6 ways you can arrange the numbers 1, 2, and 3. Now let's say we wanted to do the same thing with 1, 2, 3, and 4. Well, that suddenly becomes much harder. Not ridiculously hard, but hard enough that you don't want to listen to me read out strings of numbers for the better part of a minute. Is there a way we could make a simple formula for calculating this? Well, there is. Let's say I have balls numbered 1, 2, 3, and 4 in a hopper, and I pull them out to create an arrangement. For the first ball, there are 4 possibilities because all 4 balls are still in the hopper. Once I pull that ball out, there are now 3 possible balls that I could select. Once I pull that ball out, there are now 2 possible balls left, and then finally, there is only 1 ball left. So the total number of arrangements of the numbers 1 through 4 can be calculated by multiplying 4 by 3 by 2 by 1. Or there are 24 ways. In my first example, there were 6 ways to arrange 3 numbers, which is equal to 3 times 2 times 1. If I wanted to calculate the number of ways of arranging 5 numbers, it would be 5 times 4 times 3 times 2 times 1, or 120. This calculation where you multiply all of the numbers less than or equal to a given number has a special name and symbol in mathematics, and it's one that you might have encountered if you've used a calculator. It's called a factorial, and its symbol is an exclamation mark. If you've ever played with the factorial key on a calculator, you may have discovered that it's very easy to create numbers so large that the calculator can't handle it. Factorials are just a shorthand for multiply together this number and everything below it. To give you an idea of how quickly factorial numbers increase, 5 factorial, as I mentioned, is 120. 10 factorial is 3,628,800. And 15 factorial is 1,307,674,368,000. In fact, the numbers get so large so fast you can arrive at some surprising results. Take, for example, a deck of ordinary playing cards. There are 52 cards in the deck. How many different ways can a deck of playing cards be arranged? This is fundamentally the same problem I addressed above, just with a bigger number. There are 52 possibilities for the first card, 51 for the second card, 50 for the third card, and so on. So the answer is 52 factorial. 52 factorial is a ridiculously large number. It starts with an 8 and then has 67 digits after it. There are more ways to shuffle a deck of cards than there are atoms in our entire galaxy. Assuming that you have truly shuffled a deck of cards randomly, that means it is highly probable that the ordering of the cards in your hand is an ordering that has never existed before and probably will never exist again in history. If you shuffled a deck of cards every second since the universe began, and each shuffle was a different arrangement of cards, you wouldn't have even come within a trillionth of 1% of all the possible arrangements. The mathematical term for putting things in a particular order is known as a permutation. Now let's go back to my original example of arranging the numbers 1, 2, and 3. This time, let's assume that the numbers can repeat. 1, 2, 3 would be an arrangement, but 1, 1, 3 could be a possibility as well. This is actually really easy to figure out using the same method we did before. There are 3 possibilities for the first number, 3 for the second number, and 3 for the third number. The answer is just 3 times 3 times 3, or 27. Or to write it more succinctly, 3 raised to the power of 3. For 4 numbers, it would be 4 to the power 4, and 5 numbers would be 5 to the power 5. These numbers grow even faster than factorials do. But now let's consider a different problem, where the order of things doesn't matter. Let's say you go to a pizza place, and they have 5 different toppings. How many different ways can you make a 3-topping pizza, assuming that you don't use any topping more than once? What makes this problem different from the earlier ones is that the order of the toppings doesn't matter. A pizza with olives, onions, and pepperoni is the same thing as one with pepperoni, olives, and onions. When the order doesn't matter, this is known as a combination. In mathematical parlance, you would say 5 pick 3. To solve this problem, you first look at the number of ways you can pick 3 things out of 5. There are 5 possibilities for the first topping, 4 possibilities for the second topping, and 3 possibilities for the third topping. However, as I mentioned, order doesn't matter, so I've actually selected several redundant arrangements by doing this. We can correct for this by dividing that number by the total number of ways you can arrange 3 things, which is 3 factorial. So the number of 3-topping pizza combinations out of 5, where there are no repeated toppings, is 5 times 4 times 3, all divided by 3 times 2 times 1, or 10. Interesting side note. If you have a combination lock where you have a wheel and need to put numbers in a certain order to open it, it's actually a permutation, not a combination, because the order matters. So technically, combination locks should be called permutation locks. Let's take this idea of combinations a bit further by looking at something with more numbers that you're still probably familiar with: the lottery. A typical lottery will involve taking several numbered balls out of a hopper containing many more balls. As with pizza toppings, the order of the balls doesn't matter. Just to use an example that many people listening to this will be familiar with, I'm going to use the Powerball lottery as an example. This is a large lottery which is played in 45 U.S. states, as well as Washington, D.C., Puerto Rico, and the U.S. Virgin Islands. The game is played by selecting 5 numbers from a hopper containing 69 numbers, and then a Powerball is selected from a different hopper containing 26 balls. First, let's look at the number of ways 5 balls can be selected from 69 balls. Again, the order doesn't matter, so in mathematical parlance, we would say 69 pick 5. The number of permutations of 5 balls would be 69 times 68 times 67 times 66 times 65. We can actually make this a much simpler formula by just saying 69 factorial divided by 64 factorial. We get the 64 because it's 69 minus 5, the number of balls being selected. Again, that number contains many redundant combinations, so we have to divide that number by 5 factorial, the number of balls being selected. The result is 11,238,513 possible 5-number combinations out of 69 numbers. Those are pretty long odds, but they're actually much better odds than what you get in the actual game. And that's because there is a 6th number that comes from a separate hopper. As there are 26 balls in that hopper, and the Powerball number can match one of the other 5 numbers, we treat it separately and just multiply the previous result by 26. So, 11,238,513 times 26 equals 292,201,338. So the odds of winning a single ticket is 1 in 292,201,338, which is exactly what you will find on the Powerball website and on a Powerball ticket. Here is an interesting question. Why do they bother with the special Powerball? Why not just select 6 numbers from the main hopper instead of 5 and get rid of the Powerball? Well, take 69 factorial, divide by 63 factorial. And again, we get that number because we're selecting 6 numbers out of 69. We then take that result and divide it by 6 factorial, and the number we get is 119,877,472. If they did it that way, the odds would be more than twice as good for players, still astronomical, but much better. For most people, 6 numbers are 6 numbers. The fact that one of those numbers comes out of a separate hopper doesn't really seem relevant. However, the designers of Powerball weren't stupid, and they obviously did the math before they launched the game. They wanted odds that were long, but not too long. There are 330 million people in the United States. Most of them don't play the lottery every week. That means for any given drawing, and there are 2 per week, no one will win the jackpot, and the prize will get rolled over to the next drawing. However, when jackpots get extremely large, they make the news, and more people will play. In fact, mathematically, it might actually make sense to play once the jackpot gets beyond a certain point. A Powerball ticket costs $2, which means that once a jackpot is over $584 million, approximately, the expected value of a ticket is more than the price of the ticket. That is, of course, assuming that there's only one winner and the jackpot isn't split. So for a lottery like Powerball, you want the odds to be long, but not too long, because you want it to roll over to build excitement. We can use the same technique to determine the number of possible 5-card combinations out of a deck of cards. Again, the order doesn't matter, so it would be 52 factorial divided by 47 factorial, and then take that number and divide it by 5 factorial. The number of possible 5-card hands is 2,598,960. Significantly less than the number of ways to shuffle a deck. Of those possible hands, there are 4 that are considered a royal flush, the best hand in poker. So the odds of getting a royal flush out of 5 cards is 1 in 649,740. However, the most popular poker game is Texas Hold'em, and players get 7 cards to make a 5-card hand, so the odds aren't quite the same. The math requires a few more steps, but the odds of a royal flush in Texas Hold'em is 1 in 30,940. Exactly 21 times better than getting it in just 5 cards. So if you play a lot of poker, you might get a royal flush once or twice in your life, or quite possibly never. Permutations and combinations are something that most people never encounter as part of a basic mathematics education, but they really aren't that hard to understand. As I said before, it's all basic multiplication and division, albeit with very large numbers sometimes. There are many resources online if it's something you want to learn more about, and it's an extremely handy thing to know if you want to be able to calculate the odds of something. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Thor Thompson and Peter Bennett. I have some boostograms for you today. Boostograms are ways of interacting and supporting the show directly using newer podcast apps that can be found at newpodcastapps.com. The first is from Petar, who sent 7,777 sats on the Betamax versus VHS episode. He wrote, "Nailed it. I remember the extended VHS recording time was huge when trying to save money on tapes, and the open standard allowed for a much greater selection of films at the video rental store. I have such fond memories of those times, renting movies for the weekend. My brother and I would get to choose one, and it became a kind of competition who would pick the better film. On top of all that, the video store gave out free bags of popcorn. Life was good as a kid in the 80s. Petar, I agree with your conclusion. P Ninja sent 251 sats on the Discovery of Fire episode. They write, I believe you confuse the word discover with invent at the beginning. The first insinuates the finding of without necessarily creating, and the second implicitly requires creation. In other words, finding a burning stick in the wild is absolutely discovery. Thanks, P Ninja, but I am going to stick with my explanation that the discovery of fire is something so basic that it might technically be a discovery, but it's like the discovery of air or dirt or light. So basic that it's just a part of life, not a discovery that could be attributed to a person or, quite frankly, even a human. P Ninja also sent 251 sats on the episode about the history of wine. They ask, was the rice wine discovered in China a mead or simply back-sweetened with honey? The answer is, we don't know. The evidence was gathered from molecular analysis of ancient pottery fragments. They could detect traces of materials on it, but it isn't possible to determine much beyond that. In the research I did, it was described as a proto-wine. It might have been more of a mead with fruit, or it could have been more of a wine with honey. We don't know. Remember, if you leave a review or send me a boostogram, and my node is back up and working so I can actually accept boostograms again, you too can have it read on the show.